few molecules, for example, cis form, etc., and when you have three ethane 1,2-diamine, still it will be chiral molecule, means still it will be non-superimposable. I'm just giving you an idea about that because sometimes students remain confused. It is ethane 1,2-diamine, it is CO here, and then you have one ethane 1,2-diamine here, another one here, another one here. This is how it is shown in 2 dimensions. But if you consider 3 dimensions, this is actually how it is. This is one plane, and in this one plane you have 4 bonds of different ethane 1,2-diamine. 2 are away from us and 2 are towards us. Okay. Now see, if you see the mirror image, is the mirror image clear? Whatever is at the backside will remain at backside. Whatever is towards us will remain towards us. Okay. The only difference will be lateral inversion. Lateral inversion means left side will be right side will be left side. That will be the only difference. Okay. So how do you visualize it? So now the question is, if you rotate this by 180 degree, it should not be superimposable. That's what we say, that it will be not superimposable. For that, try to understand with this diagram. This is you have 3 ethane 1,2-diamine with cobalt, so it is actually COEN whole thrice, and then this will be Cl3 outside. I'm not talking about that. And if this is the form, this is known as lambda form. Okay, capital lambda. That is something specifically if you qualify mains and then you prepare for advanced, then this is something of relevance. Otherwise, you don't bother about what is this delta and what is lambda and what is delta form. Now, if you see the mirror image will be like this. You can visualize mirror image. Any confusion to understand this one? Whatever is at the backside will remain at backside. Only lateral inversion will be there. This is towards right side. Now this will be on the left hand side. Okay, that's the only difference. Now suppose you rotate it by 180 degree. The mirror image, this mirror image, when you rotate it by 180 degrees, then what will happen? Then it will look like this. And try to understand why it is so. Because when this is away from us, this is away from us. When you rotate it here, it will be towards us. Isn't it? Whatever is here away from us, when you rotate it by 180 degree, this will be towards us now. Is that clear or not? This point, 180 degree after rotation by 180 degree. So after rotation by 180 degree, this part will actually be towards us. Okay. This part and this part, these are symmetrical. So if there was one towards us, it will go away, and which was away, it will be towards us. So there is just inversion, but still no difference, because it was in horizontal plane, it will remain in horizontal plane. So there is no effectively any difference here. But consider this. When you rotate this one by 180 degree, this which was away from, which was towards us, will now be away from us. You need to visualize it. Okay. So whatever is towards us, so if this is towards us, you move it by 180 degree, it will be away from us. This is 180 degree angle. Is that clear or not? Okay. Now, if you compare these two, if we had seen in 2 dimensions, then obviously it looked like that they will be superimposable. Are they superimposable now? They are not. Because here this part is away from us and here this part is towards us. So that's why we say, even we have 3, normally if we consider just 3 simple bonds, they will always be superimposable. Okay. If we consider three simple bonds, their mirror images will always be superimposable. Here, it will not be superimposable due to 3D structure. Is that clear? Okay. So this shape is called lambda, capital lambda. This is called delta, and obviously mirror image is also called delta. But only if you prepare for advanced, otherwise not required. Then we talked about that the cis form will show optical isomerism. Okay. Non-superimposable. Then draw structures of geometrical isomers, because here we have 2 and here we have 4. It means this will form cis and trans. This is of M, A2, P4 type. You remember that? So these two NS3 can be on safe side, can be opposite to each other. So that's why cis and trans forms will be possible. Cis and trans. Out of the following two coordination entities, which is chiral, optically active? Cis is optically active. This is something you will remember. And the reason is very much similar what I talked about. Their 3D structures will be non-superimposable. So cis form will be chiral, optically active. Linkage isomerism, I told you that link will be different. That, for example, NCS, in one case it will be connected through nitrogen, in other case it will be connected through oxygen. Similarly for NO2, in one case through nitrogen, in other case through oxygen. Okay. So linkage isomerism means linking is different. Linking is different. In one case through nitrogen, in other case through sulfur. Similarly here, if it is connected through oxygen, then it is red complex. If it is connected through nitrogen, it is yellow complex. Coordination isomerism means coordination sphere is different. So interchanging of ligands means you have coordination sphere hold different. There are two coordination spheres here, but the ligands are interchanged. What's happening here? Now chromium is with NH3 and cobalt is with cyanide. Means the two coordination spheres are different. Coordination isomerism. Is that clear or not?
Yes.
Okay. So linkage isomerism, linking is different. Coordination isomerism, coordination sphere hold together is different. Ionization isomerism means the ion which is outside will be different. Means one will go inside, the other one will come out. So in this case, here bromine is outside the counter ion. In another case, what will happen? This will go inside and this will come out. Okay, that is the difference. The ions are different, which can be ionized. So if you ionize these, here you will get this as cation and this as anion. Here you will get this as cation and this as anion. So ions are different. Ionization isomerism. So whatever is different, that will be the isomerism. Solvate isomerism is similar to ionization isomerism. The only difference is here we will be talking about solvent. Instead of ion, we will be talking about water molecule, for example. In most of the cases, what is solvent? Water molecule. So it will look like that there is H2O here inside all, but in other case, this H2O comes outside, one chlorine goes inside. So it is similar to ionization. In ionization, what happened? One ion came outside, the other one moved inside. That's what happened in case of ionization. This is similar to that one. We don't call it ionization because here the movement is of H2O along with ion. So that's why we call it solvate. And if it is H2O, then it is commonly known as hydrate isomerism. Why specifically hydrate? Because H2O is the solvent. Otherwise, in place of H2O, if there is any other solvent, that will be solvate isomerism. So solvate isomerism is in broad sense. Hydrate is a type of solvate isomerism when the solvent is H2O. Any confusion here? So question. give evidence that these two are ionization isomers. These are ionization isomers you can identify because the ions are different. Okay, here you have SO4 outside, here you have chlorine outside, SO4 has gone inside. So how do you prove that? In this case, you know that only SO4 will get ionized in this case, and in this case the anion will be Cl minus. So you have two different ions, and if you get these reacted with BaCl2, BaCl2 will react with SO4 2 minus, and it will give you BaSO4, right? And this chlorine will not react with BaCl2 because chlorine cannot displace chlorine. Okay. So if you will use separately, you will get this reacted with BaSO4, you will get this reacted with BaSO4. The one which gives you white precipitate has SO4 outside. Is that clear? You will get both reacted with BaCl2. Because in first case, SO4 is outside, that will give you BaSO4, the second one will not. So you will identify that there is sulfate outside. It means sulfate is outside. That is SO4 2 minus is counter ion. Counter ion means primary valence ion. But if you get these reacted with these two reacted with AgNO3, so you get SO4 2 minus, which is obviously I'm talking about this one, with AgNO3, no reaction will happen. But if you get Cl minus reacted with AgNO3, then AgCl will be formed. So in this case, here no reaction, first case, and AgCl will be formed. So it will tell you that chlorine is the counter ion here. So you obtained, in first case, SO4 is the counter ion. You got it? And in second case, you got that actually Cl minus chlorine is the counter ion. So it means these are ionization isomers. Okay. So you will be given that their formula is same. They are isomers. Remember, the question is not about that whether they are isomers or not. Question is whether they are ionization isomers or not. It means it's already known that they have same formula. The question is, having the same formula, whether they are ionization isomers or not. This is the way to do that. So you get these 4 reactions done. Okay. So here it is written Ba2 plus and Ag plus. However, you can write it like this also. So Ba2 plus with SO4 2 minus will give you BaSO4 white precipitate, and Cl, if it is outside with AgNO3, Ag plus will give you AgCl, which is again white precipitate. So you will be identified that here SO4 is outside, and in second case chlorine is outside. This will give you the hint that these are ionization isomers. The counter ions are different. What is ionization isomerism? The counter ions are different. Any confusion here? Anyone not clear about it? How to prove that? In ionization isomerism, the counter ions are different, and that's what we have proved. Counter ions are different. Then bonding in coordination compounds. Valence bond theory about it. According to this theory, the metal atom or ion under the influence of ligands can use its N-1D, Ns, Np, these three. So remember the combination, okay? Write this combination N-1D, Ns, Np, or Ns, Np, and Nd. Orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planar, and so on. If D is written first, the thumb rule is if D is written first, then it will be of previous shell. That's why N-1 will be there. If I am considering in sequence SPD, then these will be of same shell. If I am writing it DSP, then these two will be of same shell, outermost shell, but D will be of previous shell. That's it. Okay. If D is of previous shell, this is known as inner complex, because D is of previous shell. So in that case, that is known as inner complex. If you are asked why, the reason is very simple. D is of previous shell. The question sometimes is asked that why only these combinations? Because these are degenerate orbitals. Degenerate orbitals, you know, they have equivalent energies. So only those orbitals take part in hybridization which have almost equal energy. And those orbitals are known as degenerate orbitals. Degenerate orbitals means same energy. I am writing same, but it is almost same energy. Other orbitals will not combine to form hybridization, to form hybrids. So hybrids will be formed only by those orbitals which have equivalent energy. Now this is thumb rule. If you have coordination number 4 means 4 ligands. Okay, on the central metal atom, there are 4 ligands. Then there are two possibilities. Either it will be sp3 or it will be dsp2, inner orbital complex, D. D is inside, dsp2. In case of sp3, the shape will be tetrahedral. In case of dsp2, the shape will be square planar. In a square planar also, you have 4 bonds, 4 ligands. But there will be 2 lone pairs, one upward, one downward. That's why it will be square planar. So, how do you get a square planar? From 4 bonds, you cannot get square planar. If you say you have only 4 bonds, then they will arrange themselves in tetrahedral shape. They will not be planar because the angle is not maximum. They should have maximum angle. So here in this case, what you will do, you can have a square planar only if it has rest 2 as lone pair. So one lone pair here, another lone pair here. Then they will keep these 4 bonds in one plane due to repulsion. So these lone pairs will repel. This will repel downward, and this lone pair will repel these upward. So they will occupy the middle position. Middle position is horizontal plane. So the 4 bonds here will be in horizontal plane. The 2 lone pairs will force them to be in one plane. This is square planar. A square planar, 4 bonds, but in one plane. And if this is the case, it will be DSP2, inner orbital complex. Then if there are 5, it will be sp3d, trigonal bipyramidal. So remember, how many orbitals are there? 5. 5 orbitals will form 5 hybrids. Okay, this is something you have done in 11th. 5 orbitals will combine to form 5 hybrids. Here 6 orbitals, sp3d2, 6 orbitals, octahedral, 6 hybrids. Then again in case of 6, there is another possibility, d2sp3, and again it will be octahedral. So remember, only in case of 4 coordination number, there are 2 possibilities, tetrahedral or square planar. For 5, it will be trigonal bipyramidal. And I hope you remember these shapes. Trigonal bipyramidal, for example, I'm just explaining PCL5, which you have done in case of 11th grade. So it was in one plane, you have these 3 bonds, and then you have another bond vertical, another one downward. And here you have, it means this is trigonal plane, horizontal plane, and one pyramid upward on this triangular base, and another pyramid downward on the same base. So trigonal bipyramidal. One pyramid upward, one downward. That's why bipyramidal. Trigonal, why? Because the base is triangular. So trigonal, bi means 2 pyramids. So pyramidal. Now octahedral is also known as square bipyramidal. Octahedral. So for octahedral, what will happen? For octahedral, say SF6. Okay. So sulfur is there. There will be one fluorine, another fluorine, one fluorine towards us, another fluorine towards us. So this is square planar. Okay. But this square planar can be possible only if we have 6 bonds. So one bond will be upward, another one will be downward. So the only difference here is, instead of trigonal plane, we have now square plane. So in this case, with this base, square base, we have one pyramid towards upward, and we have another pyramid on the same square base downwards. This is base is square, 2 pyramids. So these are the shapes we will be talking about. But here the formation of these shapes will be slightly due to different reasons. Okay? Those reasons I will be talking about later on. But the concept is very much similar of trigonal bipyramidal and square bipyramidal. Any confusion here, anyone? So now we should consider hybridization in CuNH3 whole 6 3+. How this hybridization will be there and how basically it is shown. Okay. So for that, before I start, as I said, it will be slightly different. For that, you need to first memorize this series. I said you have to memorize this series, so write it. And this is target today, that today you should be able to recall this series. Okay, it is in increasing order. I will tell you what this increasing order is. First, write it and make sure you memorize. Otherwise, you are making sure that you will not be able to do these questions if you don't memorize this one. And just pay attention to the change in color. One color is light, the other one is dark. We will be using the same thing in crystal field theory, which is part of this chapter. Okay. Later on also, here also we will be using. So it is very important that you memorize this. Yes, Samad. I'm going to tell you just first. I'm saying just pay attention that there is change in color. Different colors are there. Okay. Now you have noted down. Now try to understand. These are called ligands. These are ligands, means these can be connected to central metal atom in complexes, in coordination compound. If I am talking about the top row, these are in increasing order, but these are called weak field ligands. These are weak field ligands, and in the dark color are strong field ligands. So first you need to understand or memorize the series. This is called spectrochemical series. Okay, so if I mention anywhere spectrochemical series, this is a spectrochemical series. And this is increasing order of their strength. This is increasing order of the strength, but within that we have two segregations. One as weak field ligand, the other one is strong field ligand. However, having said that, H2O can work as strong as well as weak. In most of the cases, it will work as weak. That's why I have shown it with light color. But in few cases, I will be talking about it can act as a strong field ligand. Yeah. Otherwise, up to oxalate, it is weak. And from here, thiocyanate, it is strong. So remember the difference. SCN is weak, NCS is strong field ligand. And why we are talking about it, I will explain it. Yeah. H2O comes under category of intermediate field ligand. I told you that most of the times it will be acting as weak field ligand, but in few cases it will be acting as a strong field ligand. So it acts as weak field ligand for metals like SCTI, V, Cr, Mn, and Fe in +3 oxidation state, but it acts as a strong field ligand when metal ion is in +3 oxidation state for cobalt, nickel, and copper. So if cobalt 3, nickel 3, copper 3 has water as a ligand, water molecule as ligand, then it will act as a strong field ligand. So write it somewhere. It is cobalt, nickel, and copper. Cobalt 3 plus, nickel 3 plus, copper 3 plus. Now, don't think that how could be copper in 3 plus oxidation state. In complexes, it can be, right? How it can be, I will tell you. Why in case of complexes, there can be more bonds possible, as you can think. So you can think that copper will not have more than 2 bonds because its maximum valency could be +2. But in complexes, it is possible. Why it is possible, you will come to know in few minutes. So in these cases, H2O is strong field ligand. Now understand what we are talking about. How the ligands will be formed, how the bonds will be formed. And we are talking about CONH3 whole 6. Okay. So cobalt will be in which oxidation state here? What is the oxidation state of cobalt here? 3, right? Because ammonia is neutral ligand. So whatever charge is there on the coordination entity, the whole will be on this cobalt. So its oxidation state is 3. So to start with, what you will do, you will first write the electronic configuration of cobalt, and from that you will write the electronic configuration of cobalt 3. To understand the steps, First, you will write the electronic configuration of cobalt, and after that, you will write electronic configuration of CO3 plus. Why? Because sometimes if you consider the ion only, and you forget that when electrons are removed, they are removed from valence shell first, not reverse of above principle. Can you recall above principle we talked about? So in above principle, just to explain, okay, just to explain. Suppose I am talking about manganese. Okay, suppose I am talking about manganese 25. Okay, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Okay, 4s2 filled first, and then 3d5 is filled as per above principle. Okay, I'm not explaining it. You can draw the diagram to understand it, but that is 11th grade. So if you write Mn2 plus, what is the mistake students can do? Mn2 plus, you will say now there will be 23 electrons. Okay, 25, 2 electrons more. So you might write 4s2 and 3d3. 4s2, after that there will be only 3 electrons, which is wrong. The electrons are filled as per above principle, but electrons are always removed from outermost shell. So don't make this mistake. Reverse of above principle does not exist. There is nothing like reverse of above principle. The electron will always go from the outermost shell. It means this will disappear. 2 electrons will go from 4th shell. So Mn2 plus will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Not 4s2, 3d3. Okay, so that's why I always say that first write the configuration of the atom, neutral atom, and then remove those many electrons to get the ionic configuration. Okay, otherwise, if you can write it, you are confident, you can write it directly. Okay, so now in case of cobalt 3, okay, so cobalt, what is the atomic number of cobalt? 27, right? So you will write the configuration, okay, and then you will remove how many electrons? 3, right? So if you write the configuration of cobalt, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, how much? 7, right? 10, 10, 7. Now, if you write for CO3 plus, this is cobalt. CO3 plus means this will go away, and then 1 electron from here will go away. It means it will be the outermost electronic configuration will be just 3d6. Is that clear or not? Okay. Because otherwise you might make mistake. You can say 4s2, 3d4. You can remove the electron from here, which is wrong. Don't remove the electron from the 3d. Rather, reverse of above principle is not true. So it is 3d6. That's why you see the configuration written here is of 3d6. Is that clear, everyone? So 4s is now empty because the 2 electrons were there. They were removed. 4s is empty. After that, you have 4p also empty. So what happens? Actually, how many ligands are there? First, we look onto that. So what actually happened? To decide what happened, we see how many ligands are there. So how many ligands were there? 6 ligands were there. Okay. So 6 ligands are there. And in case of coordination compounds, I told you that these are called coordination compounds. Why? Because there are coordinate bonds. And I showed you that all the ligands actually give the 2 electrons to central metal. Do you remember that? That's why these are called coordinate bond. Okay, coordinate bond is sharing of two electrons by two atoms, but both the electrons are provided by one entity. Clear? So how could it happen here? For that, you should understand it. What will happen? There are two cases, and that's why we talked about weak field ligand and strong field ligand. So first case is you will write the electronic configuration for the central metal ion. Then you will check whether strong field ligand is connected or weak field ligand is connected. Now, ammonia is a strong field ligand. Ammonia is a strong field ligand. If it is a strong field ligand, then pairing will take place. Means whatever electrons are there, they will get paired. So these four are unpaired. Okay, they will get paired. So this was anyway paired there. This electron will move here, pairing. This will move here, another pairing. Now these two are empty. Clear? These two are empty. This 4s was empty. And these three are empty. Why I am interested in these orbitals only? Because I need 6 empty orbitals which could accept the electrons from ligands. Central metal atom has to accept 2 electrons. It cannot accept electron, except one exception. It cannot accept electrons if electrons are already there in the orbital. It has to accept 2 electrons from the ligand. It means the orbital must be empty. And we need how many orbitals? Equal to the ligands. So I have 6 ligands. It means after this one pairing has taken place, I need 6 next orbitals. And 6 next orbitals are 2 from here, D2, this S, and this P3. So the hybridization will be D2sp3. Did you get how we got the hybridization? Out of these 6, these 2 have been obtained from D. So D2. This one is 4s, so S. These 3 from P, P3. So that's why it is DsP3 hybridization. D2sp3 hybridization. Clear? Then you will say that each of these will gain 2 electrons from ammonia. And this is the final electronic configuration. Clear? 6 pairs of electrons from 6 ammonia molecules. Now the difference, if it is not a strong field ligand, the difference will be that these are occupied, so these will not be considered as free. It means D will not be there. It will start from S. The next free orbitals, S. We will consider another example for that. So this is what I have already explained. Now consider another example, hybridization in CuF6 3-. Remember, it looks like that it is similar to the previous one, but because here also fluorine 6 will be -6. So X minus 6 will be -3. X is +3. +3 oxidation state here also. And you have 6 ligands. But in this case, it is slightly different. And why it is different? The difference is here. Fluorine is weak field ligand. Fluorine is weak field ligand. So now if you write the same configuration, in this case, come back. Here pairing will not take place. And if pairing will not take place, next 6 you need, those will start from S. Then these 3P, 4. And then you need 2 from D. These 2 from D. 1, 2, 3, 4, 5, 6. It is 2 here, not 3. DsP3 D2. Is that clear? So because you have got 1 from S, 3 from P, so P3, and 2 from D out of total 6, it will be SP3D2. Easy to identify which hybridization will be there. That's what questions will be asked about. Okay. Explain the hybridization of this molecule. So you must remember which one is weak field ligand, which one is a strong field ligand, and water acts as a strong field ligand in case of cobalt 3 plus, nickel 3 plus, copper 3 plus. Clear? Any confusion, anyone? Ananya, are you clear about it?
Yes, sir.
Hmm?
Yes, sir.
Confidence is very low. Saf, is that clear? Saf, are you there? Oh, 780. Wow, 1, 2, 3, 4, 5, 6, 7 only. And 1 got disconnected right now. 11 are connected. Out of 11, 4 are sleeping or playing game. Okay, so Utkarsh, Kartike, Ayan, Arna, Savya, Tanishi, Prakriti. It means Saf. Ananya also. Ariman Paul, are you there?
Yes, sir.
Why didn't you mark the presence?
I think I left and came back. That's why I didn't.
Okay. And
Sir, I typed again. Can you just check?
Yash Bedi, you did not mark presence. When you joined, you marked the presence. Yash Bedi, are you there? बहुत परेशान कर रहा है नालायक. Not there. Okay, so those who are present and Yash Bedi and Saf specifically.
Yes, sir.
Okay, so next one, hybridization in NiCl4 2 minus. So first you will get the oxidation state of nickel. You will say X minus 4 equals to minus 2. So X is plus 2. Nickel is in plus 2 oxidation state. So you will write the configuration of Ni2 plus. Okay. So Ni3 plus, are you sure? Just let me check. NiCl4 2 minus. I think there is this misprint. There should be 2 plus. Okay. 2 plus. When you write this configuration. So after writing the configuration, what you will do, you will see whether the ligand is a strong field ligand or weak field ligand. Now remember fluorine, when I talked about, I said that is weak field ligand, fluorine. What is chlorine? Chlorine is weak field ligand or strong field ligand? That is weak field ligand. although there is some difference, obviously, then, and one more important point I will tell you. I'm just going back to explain that although there is some difference here in these two cases, but iodide is the weakest field ligand. So sometimes that is also asked. Iodide is weakest field ligand. Okay. And this carbonyl is the strongest field ligand, whatever we will talk about. So these 2 points you should remember. This is asked as a separate question as well. Now come back, we will write the electronic configuration of Ni2+. Okay. Then because we have a chlorine, pairing will not take place. So it means the 4 empty orbitals we will need beyond it. Why 4? Because we had Cl4 only. So Cl4 means there are only 4 ligands. So 4s, and after that 3p. So this S, this P, this P, this P, it will form sp3 hybridization. These 4 empty orbitals will gain 2 electrons each from chlorine, 4 chlorines. So this will be the final diagram you will show. And these are the steps you will write. Clear? Any confusion here? Next one. Okay. Similarly, NiCO4 has tetrahedral geometry but is diamagnetic since nickel is in zero oxidation state. Now, this one is very important point. When I write NiCl, and everyone pay attention here because there is some very important point here. And when I write NiCO whole 4, Cl is weak field ligand, CO is a strong field ligand, right? A strong field ligand. But here it will be nickel 2+ configuration you will write, and here you will write configuration of nickel. Because there is no charge here and CO also doesn't have any charge, nickel is in its ground state, oxidation state is 0 in this case. Getting it? So it is possible that the central metal atom can be in zero oxidation state as well. So if you write the configuration of Ni here, you will have 2 electrons here as well. I am saying NiCO4. Okay, so means Ni0. In that case, I am explaining NiCO whole 4. So it means there is no point that their pairing can take place further. They are already paired. So even if we have a strong field ligand, pairing is always done, or anyway done, already done. So again we have these 4 as empty p orbitals. So again it will be sp3. So although there is change in oxidation state, strong field ligand is connected, but the hybridization is still same. Clear, Vedant? Okay, this is the concept weak field ligand. More about it I will be talking about in crystal field theory, which is the next section. Okay, means it generates such a field that forces the electrons to pair up in one orbital. They are not able to stay separately in 2 different orbitals. So the field forces them to be in one orbital. Okay. More about it you don't need to remember. Even in IIT it will not be asked. Okay, so you just need to remember if it is weak field ligand, no pairing, strong field ligand, pairing. That's it. Okay. Then hybridization in NiCN4 whole twice. Now in this case, Cn is a strong field ligand. This one is, and you should remember all these things. Okay, I am saying again and again, otherwise you will face problem. Oxidation state will be +2, not -2. It will be x minus 4 equals to -2. So it will give you x equals to 4 minus 2, that is +2. So you will write electronic configuration of Ni2+, and you know you have already written. Okay, it will be like this. 2 unpaired electrons, and these will get paired. Now there will be difference because these have got paired. In this case, This one is empty now. This D is empty. So it will be used to gain electron. Then this S and rest 2 will be from P2. It means it will be D S P2. 1D, 1S, 2P. Clear? So you can be asked, show that this is inner orbital complex. So if it is inner orbital complex, its hybridization should be dsp2. And this is how you will show. Then in each empty orbital, there will be one Cn giving its electron. This will be the final configuration. Any confusion here? Okay, now a question. Describe the state of hybridization, the shape and the magnetic behavior of the following complexes. How do we decide the magnetic behavior? If there are unpaired electrons, paramagnetic. If no unpaired electrons, diamagnetic. Okay. So magnetic behavior, if there is even one unpaired electrons, it is paramagnetic. Okay. No unpaired, or you can say all paired electrons, diamagnetic. So diamagnetic and magnetic, paramagnetic, both are possible even if pairing is taking place, right? So try to understand. If you see these previous ones, I go back, you might be confused that if pairing is taking place, it means it has to be diamagnetic. But there might be a possibility, even if pairing is taking place, suppose the configuration is like this. Like this. Now, if pairing takes place, will you have unpaired electrons? There will be unpaired electrons now, because only this one will get here to pair up, but this will still be unpaired. So one electron can be unpaired even if pairing is taking place. If pairing is not taking place, in that case also, if it is already paired, it will be diamagnetic. But if pairing is not taking place, there are unpaired electrons, it will be paramagnetic. So remember, don't get confused that if pairing is taking place, it will be diamagnetic. If pairing is not taking place, it will be paramagnetic. In both cases, both will be possible. Okay, I have seen students making mistakes here. So in both cases, both are possible. So consider this one. CR, yes. Any question?
Even in the if we hybridize them, sir, still would there be some unpaired electrons in them?
Yes, after hybridization, there can be unpaired electrons. So in that case, the electron pair will not go in that particular orbital. The electron pair from the ligand will not go into that orbital. So orbitals can have single electron or double electron. The electrons from ligands will not go into those orbitals. Now consider this one. Cr H2O whole twice, C2O4 whole twice minus. Can you describe the state of hybridization here? It is chromium. Okay. Cobalt, nickel, and copper can have H2O as a strong field ligand. But here, H2O is weak field ligand, C2O4 is a weak field ligand. it means pairing will not take place. So I'm just going back. But I hope that you all have written the series. When I asked you to memorize, probably you have written that, but still, I'm just going back. Come back. I pressed too many times. Where are you? Come back. Okay. So H2O and C2O4 2 minus are weak field ligand, and chromium is not cobalt, nickel, or copper in +3 oxidation state. Means everything here will be considered as weak field ligand. If there is a strong field ligand and one weak field ligand, then in majority of the cases pairing will take place. That presence of a strong field ligand will force the electrons to get paired up, even if the other one is weak field ligand in majority of the cases. So here pairing will not take place, and I hope you can write the answer with this knowledge now. If pairing does not take place. So what will happen? You will write the configuration of chromium. What is the oxidation state of chromium? How do you calculate? This one will have -2. Okay. So chromium is X, H2O has 0, and oxalate has -2, and then 2 oxalates, that is 2 times, is -1. So X will be 4 minus 1, that is +3. So from here you got the oxidation state as +3. You will write the configuration. Chromium is 24. You know that chromium configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. Sorry, 4s1, 3d5. Because 4s2 normally it should be, but in case of chromium and copper there is exception. To attain a stable state configuration, half filled and fully filled, one electron is transferred from S to D. So it is 4s1, 3d5. If I write chromium 3 plus, this one will go from here and it will be 3d3. Total 3 electrons will go. So it will be 3d3 here. It means next 6 I need empty. Why I need 6? Because 2H2O and C2O4 is didentate. So it means one C2O4 will require 2 orbitals. So that's why total 6. So for that I have here D2 and then S and this P3. So configuration will be, hybridization will be D2sp3. Now you have unpaired electrons here. It means it will be paramagnetic. So due to unpaired electrons, it will be paramagnetic. And because it has D2sp3, how many total? 6 orbitals. 6 orbitals will form how many hybrids? 6. And 6 hybrids will align in which shape? Octahedral. वो paramagnetic I have talked about in chemical bonding in class 11th. Okay, but here don't bother about it. Okay. Paramagnetic, diamagnetic, ferromagnetic, ferrimagnetic, anti-ferrimagnetic, those things. Okay, but I will cover it in IIT part. Okay, JEE or NEET part. For CBSE part, don't bother about. Then CuNH3 whole twice En2. This is NH3 whole twice means 2 ligands here. En itself is didentate. 2, it means total 4. Total 6 ligands will be there. 2 plus 4, 6 ligands will be there total. Okay. Sorry, ligands are 4. Total coordinate bonds will be 6. Coordination number will be 6. However, ligands are 4. Now for that, again calculate the cobalt's oxidation state. You calculate it now. I am not calculating it. Okay. 3 plus. Write the configuration. When you write the configuration, En. Now, En is strong field ligand or weak field ligand? Strong field ligand, right? En is a strong field ligand. So in this case, what will happen? The configuration of 3D6 will be like this. Like this. Okay. Then, due to presence of En, okay, a strong field ligand, and NH3 is also a strong field ligand. Okay, ammonia is also a strong field ligand. What will happen? Pairing will take place. So this electron will come here. This electron will come here. Now these two are free. So these two are free. Then next S and then P will be free. As per above principle, these will appear free. And we will have again D2sp3 hybridization here. If it is D2sp3, it has to be octahedral. That's why I asked you at the very beginning. If it is 4, then there are two possibilities: tetrahedral sp3 or dsp2 square planar. So in that case, it can be tetrahedral or square planar. But if it is D2sp3 or sp3d2, in both cases it will be octahedral. Because there are no unpaired electrons, it will be diamagnetic. Clear? Any question here? Anyone? Any point not clear? Okay, magnetic property of coordination compounds. So again, here I will be talking about slightly, but not too much. Most of the complex compounds are paramagnetic in nature due to presence of unpaired electrons. But there are diamagnetic as well. And for paramagnetic, their magnetism is given by the magnetic moment, which is given by mu equals to square root n plus 2. Here n is unpaired electrons.